Okay, so how much do you need to know capacitance? So you need to know a few things, Cox versus VGS, and kind of the rough physical mechanisms. So this is threshold voltage. This is flat band voltage. The only thing we did not talk about is the physics. What determines the precise value of the threshold voltage? That's the type of problem you're seeing in the sample midterm 3. So we did not talk about that. That's 130 material. And likewise, what determines the flat band voltage? So most likely I'll be giving you these voltages. Now you need to know what's the capacitance value here. And if I give you enough information, what is this capacitance value? Okay, you need to know kind of what's the functional shape here. We kind of talk about that. This capacitance in the middle here, 1 over C is equal to 1 over Cox plus 1 over C depletion. So these are equivalently two capacitance in series, the oxide capacitance and the depletion capacitance. And NMOS, this is NMOS, and PMOS, it's kind of the opposite, okay, Cox. We did not specifically talk about PMOS, but they basically have a shape like this. Somewhere here is the P version of the flat band voltage, and this is VTP. Usually it's negative. This is VTN. And likewise, it's a Cox here. It has very similar functional form here. And it's important to remember Cox when you write it as epsilon over T. The epsilon is the dielectric material. If this is the gate, this is the channel or body of a transistor. So it is the epsilon of this material, and the thickness is this thickness here. And so the epsilon should be epsilon of oxide, okay? And normally I'll give you the epsilon oxide, and epsilon oxide is equal to multiplication of the relative dielectric constant of oxide and epsilon 0. This value is 3.9, but it will be given in the questions. It's very important to note it's a multiplication, not the division. The dielectric constant is always bigger than the dielectric constant of vacuum. Vacuum is 1, so it has to be bigger than 1. Right? And this is permittivity. It's also important to know this capacitance is per unit area. So the unit of that is farad per unit area. Depends on you use CGS or MKS. Is a farad per meter square. Okay. We often write some of the parameters in CGS unit, like velocity is centimeter per second. It's when you do the calculation, it's much more consistent if you stick to the MKS unit. So try use the value of epsilon 0. Usually I give you value 8.8 times 10 to the minus 14 farad per centimeter. If you convert that to MKS, 8.8 times 10 to the minus, you multiply both numerator and denominator by 100, so it should be minus 12 farad per meter. You stick everything to MKX and deal with the final answer. That's usually least prone to making the unit conversion errors. Okay. Anything else? These both per unit area or the full capacitance given the size, they all have the same functional form. They all look the same. It's the unit will be different. The scale will be different.
The capacitance of the depletion region, can it have the same area of the oxide?
So if you have a large capacitor, then they are more or less the same. So if you look at depletion, if we draw this area here, so the depletion region will be something like this. So you'll say, well, the parallel plate capacitance area width is from here to here. The depletion region is here is kind of a little bit irregular. From this course point of view, will not be dealing with this. So we'll be just asking the flat part of the depletion region. In that case, they have exactly the same area. Yes?
I have a quick question about when you do the small signal model.
Yeah.
So when you have the small signal model, you have an output resistance like RO.
Yes.
And then once that's translated to like a MOSFET circuit,
yeah.
RO becomes RO. Does it become like RO in parallel with all the other resistances? Or does RO become the other resistance?
So it depends on what the circuit is. If you have a circuit, let's say we talk many times this example. And for this example here, if this is the input, we say, okay, so G and S, and here we have a dependent current source, and this is RO. So you basically just look at the circuit. So drain is connected to, let's call this RD. So drain is connected to RD. Where is the other side of RD? It goes to VDD. VDD becomes ground. So that's why they become in parallel. And this goes to VGS, so that become your input here. Now, I can give you an example where it starts to deviate from here. So let's say I have a circuit that's like this, right? I won't tell you the name of this circuit, but let's say you're doing this circuit, VDD here is VS. So you start with the same circuit, equivalent circuit, right? And this is RO here. But now RD connect to ground. So now I will connect this to ground. And gate connected to source to ground. But my source is no longer grounded. Rather, my sources is connected to this resistor RS. So I now have RS here. And so this is kind of a strange circuit. The input actually is connected to ground, meaning it's connected to here. So it's connected to ground. This is my input. And so VGS, here is still VGS, but VGS is no longer equal to V in this case. So obviously, this is a little bit more complex to analyze compared with the top circuits. You can still do it. It's KCO, KVO. It's not really different. It's just different looking circuits. So you need to remember, don't attach RD, don't marry where the location of the resistor to the example that we talked many times, but rather just label these S and G and D and just attach whatever circuit component that comes connecting to those nodes. And so even though we haven't officially talked extensively about the functionality of this particular amplifier, but looking at an arbitrary circuit, roughly the complexity of one transistor, two transistor, and looking at the small circuit model, it's still roughly within the range of the midterm. Yes.
So will we just be tested for the transport of this small signal model?
Yeah, yeah. So what can we ask? We can ask about the gain. We can ask about input resistance. In case of input resistance, you basically look at what is the current. When we ask input resistance, basically we ask you to figure out what is I in. In this case, it's literally trivial. So this is like infinity. It's an open circuit here. In real MOSFET, or when we consider the frequency response, actually there's a gate capacitance, right? So there's a CGS here. So if we want you to consider the AC behavior, so it's not open circuit, it's a capacitance there. We'll tell you explicitly whether we want you to connect the capacitance there or not. But in real circuits, there is that capacitance. And we could ask you output resistance, okay? Output resistance. By output resistance, usually we mean you replace the input with a short circuit, and let's say the output is actually here. So you will attach test source here, and you try solve KVL, find out the current that goes through the source, IT, and your R out will be equal to VT divided by IT. So this is probably as complex KC or KVL analysis you'll need to do is, to find out something like R out. It's on the more complex side. In the problem, you'll find something that are more symbolic. We'll probably try not to have you do numerical for every problems. Some of you really don't like numbers, so some problems will be kind of symbolic. Other problems, you'll need to crunch numbers, so still bring your calculator. Okay, if you don't have any other questions, we'll call it a day here, and people who have questions, we can continue here.